All right, so section 27 is on something called L'Hopital's rule and horizontal asymptotes. So in the next section, section 28, we're going to be putting everything that we know about graphing together. So we're going to find asymptotes, we're going to find maxes and mins, we're going to find where it's concave up, concave down. We're going to have graphs of anything. It could be polynomials, you could have rational functions, like we can graph basically anything using calculus. But in order to do that, we need to first talk about horizontal asymptotes. Okay, so I know that you guys have learned a little bit about horizontal asymptotes already. Do you guys remember the shortcut? Yeah, so that's only if you have like a polynomial on the top, polynomial on the bottom, and you can use that shortcut method, okay? So sometimes things are in what we call indeterminate form. So it says, remember when we computed limits, we sometimes plugged in the values, and we got 0 over 0 or infinity over infinity. Do you guys remember those? So usually there was some kind of like factoring trick. So if we had limit as x goes to 1 of x squared minus 1 over x minus 1, do you guys remember what we did? We just factored on the top and the bottom, x plus 1, x minus 1. And the x minus 1's canceled, which allowed us to then plug in the 1. So then we would have 2, right? So originally, if we plugged in the 1, we would have gotten 0 over 0. So that's called an indeterminate form, okay? But indeterminate forms can often be made into another form, into something that can be determined. So with that, we had a factor trick. Okay, so indeterminate forms can come in several different things. Okay, so you could have 0 over 0, you could have infinity divided by infinity, right? You could have 0 times infinity, like what's going faster? Is it going faster to 0 or faster to infinity? Infinity minus infinity is not 0. It depends on which one is bigger. 0 to the 0, right? We don't say what that is. Infinity to the 0 and 1 to the infinity. Okay, so there's lots of different things. Yes. It would not, because these are limits, remember. So if something is going towards 1, it's like which is going faster? Is the power going faster? Or is the thing going to 1? Okay. So all of these are indeterminate forms. Okay, so for 2 of them, 0 over 0 and infinity over infinity, there's something that we can use. Okay, and this is called L'Hopital's rule. I know it looks like hospital. There's no S in there. It's French. So this guy came up with this rule, which is a very, very quick way of doing limits. Now, this is not tested on the AB exam, but it should be, right? Because it's super simple, and it helps you solve a whole bunch of limit problems. Okay, so even the ones that we did in chapter 1, like you could even solve them with L'Hopital's rule. Okay, as long as they're in the form 0 over 0 or infinity over infinity when you're plugging the numbers in. Right, so suppose that f and g are differentiable on the interval a to b, except possibly at some fixed point c. And suppose that the limit as x goes to c of f of x over g of x has the indeterminate form of 0 over 0 or infinity over infinity. And you can have positive or negative infinities, it doesn't matter. It could be positive over negative, negative over positive, positive over positive, whatever. Then the limit as x goes to c of f of x over g of x, it's really weird. You end up being able to just take the derivative of the top and the derivative of the bottom, which seems to go against all derivative rules ever, right? Because it's like, wait, shouldn't I do quotient rule if I'm going to take the derivative? Right? But it's just a limit, right? It's a rule that involves limits. So you're allowed to take the derivative of the top and the bottom for L'Hopital's rule. That's what it's going to equal, yeah. And you could continue to go, like you could do second derivative if needed and so on. So you'll see some like that. So for example, if I have limit as x goes to 0, 1 minus cosine of x over sine of x. Okay, maybe you don't know any factoring tricks here. There would be a trick, like you could multiply by 1 plus cosine on the top and the bottom, because then you would get 1 minus cosine squared. Do you guys remember what 1 minus cosine squared is? Sine squared. So there are tricks to do this, but maybe you don't know them, right? Then that's when we try L'Hopital's rule. So if you plug in 0, so we would get 1 minus cosine of 0. What's cosine of 0? 1 all over sine of 0, which is 0. So we end up getting 0 over 0. So we first check to see if it is one of those indeterminate forms. And it is. It's 0 over 0. So if that happens, we do L'Hopital's rule. So I always indicate that I've done L'Hopital's rule by doing a little equal sign with an H above it. Okay. So we're going to have limit as x goes to 0. And we take the derivative of the numerator. So it's the derivative of 1 minus cosine of x. Maybe 0. Yeah, the derivative of cosine is negative sine. So it's going to be minus a negative sign is sine. And the derivative of sine? Cosine. Now we try again. Can we plug in 0 now? So when I plug in 0, I get sine of 0 is 0. Cosine of 0 is 1. So I end up getting 0 over 1, which is actually 0. So that's your answer, 0. If you got 0 over 0 again, you'd repeat the process. You keep going, okay? Yes, Patrick.
So does that mean one of the answers more correct?
What do you mean one of the answers is more correct?
Like 0 over 0 or something?
Yeah, that's incorrect. Like 0 over 0 is what we call an indeterminate form. It's just like our factoring one. Do you remember this one? Like this was 0 over 0. Was that the answer? No, right? You had to do some kind of trick to get the actual limit. Okay, so that's why we call it an indeterminate. We can't determine from the information right now, but we can always do some kind of trick. Yeah. 0 over 0 or infinity over infinity. It has to be one of those two things. All right, so this one. So if we plug in 2, right, the top we get 0. The bottom we get 4 minus 6 plus 2. We also get 0. So it's in one of those indeterminate forms, 0 over 0 or infinity over infinity. So we do L'Hopital's rule. So we take the limit as x goes to 2, and we take the derivative of the top and the derivative of the bottom. So the derivative of the top is 2x. The derivative of the bottom is 2x minus 3. Now can you plug in 2? Yeah, so if I plug in 2, I get 4 over 1. That means your limit is 4. Now this works if you did the factoring thing too. Like if I do the limit as x goes to 2, and I have x plus 2 and x minus 2, I factor the top, and I have x minus 2 and x minus 1, I can reduce out. And when you plug in 2, what do you get? 4 over 1. You get 4, right? It still works the other way, but this is another way of doing limits, okay? The convenience of L'Hopital's rule is it works for things that we can't factor. We don't have these factor tricks for. We're going to have things like e to the 5x, right? We're going to have crazy things that maybe we don't know a trick for, okay? This is the one that I made you guys memorize a long time ago. Do you guys remember what this is? Yeah, it's one. So if you didn't memorize it, this is what I always have to do because I never memorized it. So I still, to this day, think about L'Hopital's rule. And I'm like, okay, if I take the derivative of the top, I get derivative sign is going to be cosine, right? Right, you guys all see it is 0 over 0. Keep putting 0. Okay, so I get limit as x goes to 0, I get cosine of x over 1. So when I plug in 0, what do I get? 1. Right, so our answer is 1. So you could quickly do it with L'Hopital's rule. Same for the other one that I had you guys memorize, the 1 minus cosine of x over actually do also do L'Hopital's rule. All right, so next one. So I have limit as x goes to infinity of x over natural log of x. Okay, so this is in the form infinity over infinity. Okay. If you can think about which one goes faster, sometimes it helps on these. Okay, can you think about, like, is the numerator going faster to infinity or is the denominator? Remember we've done this before when we did like natural log of like 10 billion on our calculator. It goes very, very, very slowly. It's like 13. You're like, really, 13? But I don't know what it is, but yeah, it goes super, super slow. So think about it. Is the top or bottom going faster? The top is. So it's kind of like top heavy, right? It's bigger on the top than it is on the bottom. What do you think it's going to go to? All right, you kind of logic through it. It will go to infinity. So let's see why. So it's in the form infinity over infinity. So we're going to go ahead and do L'Hopital's rule. So when I take the derivative of the top, I get 1. When I take the derivative of natural log of x, I have 1 over x. So I simplify. I don't like to see the fraction within a fraction. So I have 1 divided by 1 over x. What does that become? X. So the limit as x goes to infinity of just x. Plug in infinity, you get infinity, right? All right, same idea on this one. So this is pi. So limit as x goes to pi from the left. So if I plug in pi on the bottom, I get 1 minus cosine of pi is going to be what? What is it? -1. So what do we get on the bottom? 1 minus a -1. And then sine of pi, I get sine of, or I get 0, right? Sine of pi is 0. So I have 0 over 2. That's your answer. Your answer is then 0. Okay, so we did not get 0 over 0. So be careful. Always check to see if you have 0 over 0 or infinity over infinity before using L'Hopital's rule. Okay, so what if we had something similar. What if we had sine of x over 1 plus cosine of x? This is the one that gives us 0 over 0, right? Does that make sense? Because we have 1 plus a negative 1. So when we do L'Hopital's rule, the derivative of sine is cosine. The derivative of 1 plus cosine of x is negative sine of x. So it's a little tricky. The top gives you what? Negative 1, right? And bottom gives you 0. So this is one that's probably going to like infinity or negative infinity because of that. Okay, so it's not in this indeterminate form. Okay. It's going to be one of them, yeah. So let's use a, what would be the best way? I think on your homework, I let you use the calculator on the back side for tricky ones like this. So we'll use a calculator. And we're going to approach pi from the left. Okay, so go ahead and get your calculators out. It's not an assignment, you have another assignment. Yeah, that's why I gave you time to work on it in class. Yeah. Good thing. Oops, how do I get a 3 in there? All right, so we're going to go to our table. I'm going to make sure I'm in radian mode first, because I've been doing this in pre-calc too. So we want to get really close to negative pi. Okay, so not negative pi, really close to pi, right? From the left. Okay, so pi, we know is around 3.14 something. I could give you more digits, I'm not. All right, we're going to come from the left. So what do we want to plug in? Things like left. Yeah, we want to plug in, let's say, like 3, 3.1, 3.14, right? We want to get closer and closer. Does that make sense? And let's see what's happening. So maybe we can even start with 2.5. So 2.5, 3, 3.1. Whoops. I hit something. Oh, goodness. I hate this calculator because I always have to type everything in. Yep, so we're approaching from the left. Does that make sense? The left of it? Okay, so 3 point. So what's happening to our numbers? Where are they going? To infinity. Right, exactly. Okay, so let's think about how else we could do this. What if we didn't have a calculator? So it is going to infinity. All right, when you see cosine over negative sine, what function is that? Cosine over sine is cotangent. So what we're looking at is negative cotangent of x. Okay, do you guys remember what cotangent looks like from your graphs? We did this a long time ago. We did it in pre-calc, right? So let's think about it. Let's think about where it's undefined. So it's undefined whenever our sine value is equal to 0. Well, sine is equal to 0 at 0, pi, 2 pi, and so on. So that means that we have vertical asymptotes at 0, pi, 2 pi, and so on. Okay, so negative pi. All right, and then cotangent usually goes like this. Okay, but we have negative cotangent. So what way do you think it's going to go? The way tangent goes, yeah, it's going to look like this. All right, and you can test some points, like you could plug in like pi over 4 and pi over 2 and get some different values. Right, but it does go like that. So as you approach pi from the left, that's right here. Okay, what do you get closer to? Infinity. So there are other ways to get it. Okay, so if you didn't have your calculator, if you had already done L'Hopital's rule and you were like, it's not 0 over 0 anymore, what do I do? Then you can think about what the graph looks like too. All right, so this one. so limit as x goes to 0. So if you plug in 0, you do get 1 minus 0 minus 1 all over 0. So you do get 0 over 0. So that means that we can use L'Hopital's rule. Okay, so we're going to do L'Hopital's rule. So we're going to have e to the x minus 1 over 2x. So now when I plug in 0, what do I get? Still 0 over 0, right? So we do it again. So we get e to the x over 2. So what's our answer? 1/2. E to the 0 is 1 all over 2. Yep. All right, same idea with this one. So if I plug in 0, I get natural log of 1, which is 0 over 0. So I'm going to do my L'Hopital's rule. H is funny. So I'm going to do limit as x goes to 0. I'm going to have 1 over 1 plus 7x times 7 all over 1. Yep. So I can kind of simplify, and a lot of times you'll have to simplify because there'll be weird ones. Okay, so you're going to have 7 over 1 plus 7x. So when you plug in 0, what do we get? 7, that's your answer. Okay, easy. Do you guys like L'Hopital's rule? It's not that bad. Nick Chula used to call it Hippo's rule. I don't know why. Hippo? Like, I don't even see hippo in that word. All right, so if you do this one and you bring it to me next time, I'll give you a bonus point. It's a hard one. I did it last year in class, but it is pretty tricky. You have to show all of your steps, though, because it's going to be one where you're going to have to keep doing it, right? All right, so it says, notice L'Hopital's rule did not cover all of the indeterminate forms. It only covered 0 over 0, infinity over infinity. So what if we have infinity minus infinity, or 0 to the 0, or 1 to the infinity, or whatever? The goal is to get it into one of those two forms that we know. Okay, so if you can do that, then you'll be good. We don't do a lot of this in this class. So it says you use L'Hopital's rule to help you find the horizontal asymptotes and or end behavior of the following functions. Okay, so this is, your homework has something about horizontal asymptotes. So horizontal asymptotes, when you find that, you need both the limit as x goes to infinity of your function, but you also need the limit as x goes to negative infinity. So we've talked about that before. Remember, you can have two different horizontal asymptotes. So we're going to find both. So we're going to find the limit as x goes to infinity of x squared e to the negative x. Okay, so if I check right now and I plug in, I'm using this lightly, plug in, air quotes, infinity. I have infinity squared, which is infinity. And then I have e to the negative infinity. What do you guys think e to the negative infinity is? What is it? Not negative infinity. It's e to a negative big number. So 1 over e to the big number. It goes to 0. That's in the form. Okay, that's the form that we're in. So we don't know. Infinity times 0. Which one's going faster? We don't know. Okay, so what we do is we rewrite. Any ideas on how to get this to look like a fraction? It's very easy. Just put that e to the x on the bottom. Now it's infinity over infinity. All right, so when I take the derivative of the top and the bottom, so I do L'Hopital's rule, I get 2x over e to the x, still infinity over infinity. So I do it again. So I get 2 over e to the x. So what does it go to? 2 over a really, really huge number. 0. Yeah. So the first horizontal asymptote is 0. So now we have to do the other one. It's no fun, right? We don't like doing both of them, but you gotta. Okay, so how about this one? So when I plug in negative infinity, a negative huge number squared is going to be a huge number, right? And then we have e to the positive infinity now. So we really have an infinity times an infinity situation. If you have infinity times infinity, there is no doubt what that is. What is it going to be? You've been saying it for years to your brothers and sisters, right? It's going to be infinity. Does that make sense? Right? It's the only thing you can possibly be. A huge number times another huge number is a huge number. Do you guys see how that worked? Because this was now e to the negative infinity. Yes. Right, you don't need L'Hopital's rule because that is not one of the indeterminate ones. Okay, it's not one that we have a question about, right? All right, so that's going to be one where on the right side of the graph you're going towards 0, and on the left side of the graph you're going up to infinity. Okay, so that's like the end behavior of that graph. So we do a little sketch sometimes, that's useful. All right, so this next one, so I have g of x equals x times natural log of x. So think about limit as x goes to infinity. What do you guys think? Natural log of infinity, what is it? It's infinity. It just is one that goes really, really slow. We've talked about that before, okay? So we do have infinity times infinity, right? So that's fine. It's infinity. So on the right side of the graph, as x goes to infinity, we go to infinity. So we're going up. But we still need to figure out what's happening on the left side of the graph. So as x goes to negative infinity, what do we think for this one? One would think that it's negative infinity, but that natural log is throwing us off. What's wrong with the natural log? What'd you guys say? No? You can't take the natural log of a negative number. So this one actually does not exist. There's nothing on this side of the curve. It's like totally blank. Does that make sense? Because you can't take the natural log of a negative number. Yeah, Carrington. I'm just curious, because natural log is not the same as 1 over x. Its derivative is 1 over x, right? So you can do that, yeah. All right, so let's see what that graph looks like. I'm curious. So if I do x times natural log of x, see how it just kind of ends on the left side. Does that make sense? So there's not a horizontal asymptote coming from the left side. Okay? All right.